Okay, so why don't we go ahead and get started. It's just afternoon here in the Eastern US. Would like to thank everybody for joining the first webinar from the US office. Glad that everybody can make it. Good morning, good afternoon, good evening, depending on where you're joining from. So with that, why don't we go ahead and get started? So let me go ahead and click here. Okay, just a quick note. Everybody's probably been used to using GoToMeeting or GoToWebinar for a while, but if you have any questions, you can just type them in the question panel, in the control panel, kind of showing you where that is on the slide. So now if we go in, just kind of give you a quick agenda as far as what we're going to be covering today. First, we're going to introduce the US team. So that in case you don't know us, you can kind of put a face with the name. Then we'll talk briefly about what IDEA StatiCa is and kind of how it works. Then I will hand off to Andrea, who will go through a couple of examples of connections within the software. So as I said, my name is Dave Eckroat. I'm the director for the IDEA US office. I'm here based in the Philadelphia area. I've been in structural engineering for 28 years, which is hard to believe that it's been that long at this point. But just really happy to be here. And I'll introduce Jan Gugon. He is our regional engineer for the central US. Jan, do you want to say something?
Yes. Hello, everyone. This is Jan. Yes, I'm a regional engineer for the center region of the US. Coming from France, as you probably can hear it, and I've moved to Chicago 8 years ago, did my master's here, and then I started working as a connection engineer in Chicago for DZSC, Drucker Zechdel Structural Engineers, and I joined IDEA StatiCa in November of last year.
And then next, we also have Andrea Castello. She's our product engineer. Andrea?
Hello, everyone. Well, I am Andrea, and I will be supporting all our US users with all the technical questions, emails, or cases that you upload there. So I am civil engineer. I have a structural engineering master, right? And yeah, I have well, less years than David in this industry, but I have around 6 years into the structural engineering industry and also software industry. So, well, feel free to reach to that email that you're seeing in the screen. Thank you for being here.
Sure. And so, I mean, this is just the beginning of our team. We will continue to grow in the US as we need to. So with that, I'm going to actually turn off my webcam, just kind of make it a little easier to stream for everyone. And let's get into the presentation. Okay. So, I mean, first thing that I just want to talk about is just some pain points. So, I mean, during my time in structural engineering, you know, I've come to notice that something's related to connection design. A lot of engineers use hand calcs. They're relatively easy to do following the AISC equations. But once you get in outside of the kind of the code equations, you need to use some engineering judgment to kind of understand how that connection will actually work and how to design it. And then, of course, the most important part of that is that, you know, hand calcs are time consuming. And let's face it, nobody has spare time these days on projects. You know, next connection software, they're definitely faster than maybe hand calcs, very easy to kind of manipulate if changes happen. But again, kind of similar limitations as hand calcs as far as, you know, typically they're focused on the code equations. And once you get outside the parameters of those, it can become more and more difficult, or, you know, kind of have to kind of simplify things or justify some things to be able to use those software to design some of the more complex connections. And finally, I mean, projects are just becoming more and more complex. You know, more and more complex. your budgets and schedules aren't getting any shorter or any longer, rather. They just keep shrinking. So it's just important to have tools that can handle these types of scenarios. And then my last point is just that, realistically, most people are using multiple analysis tools, BIM tools, detailing tools for a project. And really, you do need a tool in connection design that can link to all of those different software. And that's one thing that IDEA has really been focused on, as far as just being able to link with other industry partners and really be kind of a central piece for connection design. So what is IDEA StatiCa? Obviously, it's a software for analysis and design of steel connections. It does use finite element analysis for the analysis, and that means that it has a lot of flexibility in being able to design or analyze and design connection configurations that you really can't do any other way. In addition, we do have some AISC code checking related to it. It's really, when you look in the commentary one, there are multiple references of allowing the use of finite element analysis to replace the code equations, specifically for connection design. So how does it work? So really, IDEA, once you build your model, you go to click analyze or calculate, and it is going to break up the members into plates, your plates and angles, all into finite element. And that's all done automatically. And then it's going to start to calculate the stresses and strains in those finite elements and use those to compare to the material properties that you're using. This is doing nonlinear analysis. Once the software has that analysis, it looks at the bolts as nonlinear springs, and as well as the anchors. And the welds are broken up into finite elements as well. The nice thing is that once the analysis on these components are done, they are actually compared with AISC code equations. And that's easily viewed right within the reports and even on the screen. One thing to kind of note, we do look at the stresses and strains. So once we get past the elastic range, there is a small amount of plastic strain that is allowed within the software. That's obviously from our European background. Eurocode allows a 5% plastic strain to be used. Our core, what we've been doing is we've been verifying those analysis results and kind of confirming that 5% strain limit actually correlates pretty well with the code equations. And part of how we've been doing that is we've been working with a bunch of universities. So you can see here 3 universities along with other partners to do some verification from the software. So they're building models in IDEA, they're running hand calcs, sometimes even running some finite element models in much more advanced, or maybe not necessarily advanced, but different finite element programs like ANSYS and Abacus, and when possible, comparing that with actual physical results. And what we found is that, the correlation between what IDEA is providing, on these relatively simple connections and what you're getting out of the code equations, it's very tight correlation. So you can have confidence in that the results that you're getting within IDEA are going to align with what would be done through the code equations. And again, just kind of talking about it, since we're doing finite element analysis, we're looking at the entire joint. So, all 3 dimensions is being run in the analysis. So that could potentially be a time saver for you, and that you're not breaking up into planar connections and looking at multiple connections. It also gives you an understanding of the behavior of the overall joint. With that, we have a lot of section databases, pretty much for every rolled section that is out there in the world globally, as well as obviously the AISC is included in that, allowing you to use built-up shapes, some templates that allow you to kind of build those very quickly, as well as a general section editor that kind of lets you build up a very custom section if need be for your designs. One of the real strong suits with IDEA is for HSS connections. The interesting part is that yeah, I came on board last summer, and I think December, January timeframe, we got an email saying, hey, did you see this article from Steel Tube Institute? They actually put together their own study of software for HSS connections. We had no idea this was happening, but the results were all the different connection types that they were looking for, IDEA was able to design. And there are some connections in there that IDEA is the only way to design it. So that was just awesome to hear, and really kind of justifies what we're doing. That we're providing a tool that's really is used, and needed in the industry. So if you'd like to read that article, it's right on the Steel Tube Institute website, or just contact us and we can send you the link to it. When we start to look at analysis types within the software, obviously we spend a lot of time talking about stress and strain. That's your kind of general analysis for connection design. We also have some buckling analysis included in there. We're actually doing some verification work with Bo Doswell that should be released shortly. Also, you can look at stiffness analysis. You can look at capacity design for high seismic connections, kind of understanding if your hinge is in the correct spot, and kind of making sure that the analysis is correct. And then we have a design joint resistance. This is a really, frankly, cool tool. It allows you to kind of build a connection, apply some nominal load to it, and the program will iterate and run to kind of determine the overall capacity of the connection. This can be very helpful when you're looking at maybe existing buildings and having to change of use, or maybe some, adding some floors, just making sure that the connections all work within the design, instead of just automatically starting to reinforce the connection. So one thing I just wanted to kind of show, as far as linking to other software, I mentioned that earlier. So you can kind of see the usual players that we've worked with over the last couple of years. Two new additions are RISA 3D. So from RISA, you can actually export an SAF file format, and that can be read directly into the checkbot, which is our linking application to connect into IDEA connection. The challenge with that is that it is only going to be sending out the geometry and shapes sections. You will not get any loading from that SAF file format at this point. And then the real exciting news, something that I felt was really missing when I came on board, in version 22, which should be out in a few weeks, definitely in the month of April, we will have a direct link to RAM structural system. So you'll be able to bring a RAM model directly in the checkbot as the entire structure, grab connections, drop them into connection, and design them. So definitely a lot of excitement going on there. I think with the RISA and the RAM additions, in addition to ETAB, SAP, TSD, STADPro, we're covering the vast majority of the analysis tools that are being used in the US market. As far as detailing, we have advanced steel. We obviously have links to Tekla. I can tell you last week I spent a good amount of time talking to the folks at SDS2, and we are definitely in the process of getting a link so that you can link SDS2 to IDEA as well. So definitely looking at being able to take your models from whether it be BIM or analysis and bring them into IDEA to kind of just help streamline your processes and save you time. So with that, I will actually hand it off to Andrea, and she gets to do the heavy lifting for the rest of the session. Thanks for taking the time.
All right, David, can you see my screen just to?
I'm seeing the opening screen for IDEA.
All right, perfect. Yeah, that's what I wanted to show. All right, thank you, David, for that introduction. I will jump into IDEA StatiCa, and I will show you two examples maybe there are some users, right? So it is important for us that you, at the end of the session, you can send some options or some suggestions for the future webinars, right? So, okay, so for today, I will go to the connection application within IDEA StatiCa, and then I will start the model from scratch. But here you can see the initial screen of IDEA, where you can start selecting the class of well, connection you want to start, right? So we have, in this case, beam to column. Then we have the second section that it's geometry, right? So you have some geometries here. Then I will select this one, because I want to do a moment connection from beam to the web of the column. Then in the third section, you will see some templates that are already built in here, right? So I will not use those, but those are available there. So if you click there, you can have a snapshot of what is going to be constructed in IDEA, right? But also you always have the blank connection, so you can, well, put your own design there, right? So here are some parameters that you can change, but also after you can change that. So I will hit create project, and that will bring only the members, right? With any template, as you can see, we had templates there that after you can modify, of course, right? So here, this is the main interface of IDEA, right? I am in the design tab. So you can click in any member, right? And you will see all the information in this left side, right side of the screen, right? So I am manipulating this C member, right? You can change names of the members, so it is easy. Well, it will be easier for you to identify those members. Okay, so I will change this section. Okay, so as you saw, I click into the plus icon, then I come to the shapes options. Here I have the wide flange AISC database, but this is under my favorite tab, right? So then you can go to the all tab, and then you will see all the databases we have. These are from around the world, right? So if you go to the favorites, well, if you want some of the databases into the favorites, you just need to click in the star icon. Then I will come back here. I will select 14 by 53 wide flange section, right? So you find it here, and then you can change the material from here as well. So you click here in the add icon. I will select this I-9092. So I click OK, OK, and then that is changed. Okay, so then I will also change the B section, or the B member. So that will be 14 by 48. So I scroll down until I find the one that I want to use, and then you just click OK. Let's say you forgot to change the material. You can change that using this edit icon. All right. So once you select one of the materials, you will be able to select from the drop down menu. Okay. You hit OK, and the same for the sections, right? If you use one, that will be there in this drop-down menu. Then if you want to have a cleaner file, because those ones are the ones that just came in, but I'm not going to use it anymore. So I go to the materials tab, and then you can go to your cross sections and then delete the ones that you are not using. So that will do like a clean file. Then if you want to add more members, you can just click here in the member icon. Sorry, and then that new member, it was located at the same position of the B member. So I can rotate that one, the new M3 member, right? I will put 90 degrees into the beta direction. So that is the angle around vertical z-axis, right? So I will use minus 90. So I have that one in this side. So as you can see, you can add many members as you want, right? So you can edit the position of these members using aligning in node or aligning to member plate. Okay, so now that we are okay with the members, let's start adding some connections, right? So for doing that, you have to click here in operations. These operations will help you to add the connections or your specific connections, right? So we have 24 operations that are divided into 2 categories. One category contains those connections that are already built in, like let's say end plates, fin plates, base plates. So that will fit into the members that you already have there. But we have also a second category of operations, and those are the ones that will help you to construct very specific connections that may need 2 or more operations to achieve the desired design, right? So those are like standalone operations like bolts or welds, or just adding a stiffening plate, and then you can edit the parameters and locate wherever you want to use that plate, right? In this case, I will use firstly the end plate operation, then the bolts information are required to input, bolt grade and diameter, and then you hit OK. So that end plate was already, that was drawn into, in the beam member. I don't want to put the beam member, I don't want to use the beam member for that end plate, so I will change that member to M3. That it's the member that I want to use, right? So this end plate is related to one member that it's M3 and also connected to member C that it's the column, right? So this operation has everything to modify and manipulate this this connection, right? So as I said, this is built in with all the necessary to that end plate, for example, bolts and welds, right? Also, this the good thing of this operation is the predesign button, right? So here you have some options to predesign this this end plate. Let's say this is the flush option, but also you can select the extended one, so that's automatically changed, as you can see here, right? I will leave the flush one, right? So some of the operations have this predesign option. It's very helpful to modify it in an automatic way. So you can edit those parameters from settings for the predesign option, and here you can set up those parameters for the predesign. Okay, so all right, so let me go into the bolts. These bolts are within the end plate operation, right? I will change this view also to transparent, so it is easier to see the location of the bolts, right? So the way that bolts works in IDEA StatiCa is the next. So always you will have an reference either coordinate or reference either in this, like in this input, that you have the top layers, left, bottom, and right layers, right? So I will delete this just to show you how this works, right? So for the top layer, our reference will be the top flange of the beam, right? So if I start typing, let's say 1 inch, and then you can see that this was drawn here 1 inch, but because it doesn't have any horizontal coordinate, you don't see that ball. But then if I write 1 inch in the left layer, that my reference for the left layer will be the left edge of the end plate. Here you can see the 1 inch, right? Then the bolt is round there, right? But I always like delete everything so I can learn how to add those bolts, right? So in this case, it is outside of the end plate, so I will use negative, let's say, coordinates, right? So you can see how that's modified. So let's try with 2 inches, right? So then you can see how that is well working, right? So then if you want to add a right layer, so the right layer input will be, well, the reference will be the right side or the right edge of the end plate, right? So in either way, if I put -2 inches, you will see that distance here, or you can change that so you see that reference here, right? That is saying 3 inches. Then the same happens with the bottom layer. The reference for the bottom layer will be the bottom surface of the bottom flange, right? So if you put 2 inches, right, that will be in the positive direction. So let's use -2, right? So that's how it works. And then if you want another row in the top layer, then you can just type on space and then -2 inches from the actual layer that it's already there. So you just click there, and then you will see the next row from the last bolt. So you have this 2 inches that you input there, right? So I always recommend to do that, like delete everything and start typing to see how it works. So it is easier to you to understand how bolts works in IDEA, right? So you can delete this, and I will use the flush Predesign. So I have the bolts that were built in at the start. All right, so we're okay with this. Well, also welds are there, right? So you can change here the leg size and the type of weld that you want to use. Okay. Then for this connection, I will use the second category of operations that are like standalone, right? So for that, I will add some stiffeners, and also I will add a shear plate, extended shear plate for this connection, right? So I'll go to operations, and then I will add a stiffener there. So these stiffeners are located on member C, related to B, right? So that's related to, well, the position of the flange B, and also, well, the 2 flanges, okay? So you can increase here the thickness, and also just put the stiffeners in the front side of the column, or rear side, or both, okay? I will use both. And then, as you can see, if you change to the solid view, you can see that those, well, the flange is overlapped with the stiffener. So for that, I will use an operation called cut, right? So that will cut a member with reference to something else, either a member or a plate. So I will cut member B, and that member will be cut by a surface, well, a plate in this case, and that plate will be, the first cut will be this plate, right? So how do I know what is the name of that plate? Well, you just hover the mouse into this member, and then in the left lower side of the screen, you will see the name. This is called stiff 1D, right? So I will select that one, stiff 1D, and then I will select surface, right? So if you see here, if I put transparent view, now the flange is cut, right? And then also welds were input, so you don't need to add another operation of adding welds. So this is like a better way to do welds, because you're cutting with reference of something, and then you're welding that cut, right? So you can see here the weld from the stiffener to the flange. So then I will do the same for the bottom flange. So I will copy this cut operation, but then I would just change the stiffener. So this is a stiff 1B, and you have also here the cut, right? So this is an easy way to do that cut. We have more ways to arrive to the same result, but as you're using the software, you will learn to, well, these tips, right, or these tricks. All right, so I will then use operation and a fin plate, or well, shear plate. I select that one, and then automatically was input into the member B, right? But I want an extended shear plate. I will use this view so we can see everything from here. The bolts that are in the back are the ones for the end plate, right? So you don't confuse yourself, right? So I will add, let's add a gap of 4 inches here, right? As you can see here. So that is the gap that was added. Here you can see the dimension. And then this is the distance. Well, this is the overlap, right? So that's the distance from the beam to the end of the shear plate. So you can increase that one, right? Let's say some inches there, right? So that was increased. Then this is the offset for well, from the top flange, or well, the top flange and the bottom flange. So if you put 0, you will see the complete shear plate. So I want that one to start from the bottom surface of this flange, so that it's minus the thickness of that flange, that it's 5/8. So the same for the bottom part, minus 5/8. Okay. So here you can also add more bolts, right? So you have that, and then instead of having 2 3/16, I will add 3, right? 3 inches between them. All right, then what if I want to edit this plate? Well, this shear plate. You can go to the editor, right? And this is the plate editor. So you have that option, the editor, for some operations, and then you can add operations to that plate. Okay, so either you can modify the bolts from here if you explode it, and then you just use coordinates. Sometimes when you have a tricky arrangement of bolts, you can use that, and it's easier, right? But also, well, in this case, I will add a notch operation to corner. Well, that's located using this number of corners. So I will use corner 2, right? And then I will add 4 inches in this direction, and the height will be 1. And then I also can copy this operation, notch operation, and that one will be in the corner number 3, and I will just invert the dimensions here. Okay. I like also to show this. If you go to the drawing tab, you will see the drawing of that plate, and then you can just right click here and you can send it to DXF, right? So this is very useful. Well, DXF, it's a file that you can open in any CAD software. Okay, so you just click on apply and then OK, and then you will see that notch in the plate, right? I can put more detail here, but because of time, I will let it as it is, right? Then, okay, so now I think we're good with this. We can start doing some testing, right? But before going and calculate this, I need to add some loads, right? So you can go to the load effect. So here I have only one load condition. You can add loads as you prefer, clicking here. So we always recommend to add the load combinations you have for this joint, not just the critical one, right? So it is, well, you have an accurate model if you add more load combinations rather than having just the worst case, right? Also, you can use the import and export option to bring the loads from your global software. But if you saw the software that you are using in the slide that David showed, also we have that option to use checkbot, right? So it is easier to bring all the geometry and the loads from your global software, all right? But anyway, I will use just this example. So the M3 will be a moment of 100 kips, and here you can see the load that it's drawn in the visualization area, and that will be minus 40 shear force. Okay, and then for the M3, sorry, B member, that will be 45 kips and minus 20 kips for shear force. 45 kips fit, right? So also, when you're starting to use the software, sometimes you don't get everything connected, right? So to avoid that, or to avoid an error in the analysis, you can go to operations and right click under that operations tab, and then you can click on check missing welds. So that will tell you if something is not connected, and that will add a weld automatically. So it is very useful to check if everything is okay, right? Then, okay, I think we are ready to calculate this. Let's see how it goes. All right. Okay, well, this run, I would like to bring this slide that will help us, to you and me, right, to review results, right? So here I have a results checklist. It's like a process to follow when you're reviewing results. I will always recommend to review the deformed shape and ask yourself, is it behaving as you were expecting, right? Then after you see that it is okay, you have a good deformation, well, not good deformation, but correct deformation, then you can go and review results in the order of the tabs. I will show you that. And then if you're changing some things of the connections, I always recommend to activate the stop at limit strain. That will help you to reduce the time of analysis, because that will stop the analysis whenever you have a failure, either in plates or bolts or welds. Okay, so that will help you when you're doing tests. Then once you're okay with that, then I recommend to recognize the controlling failure, and from there modify the model and test it again, right? So it is like a circular process. So let's see if that already ends. Yeah. So here, let's see what it's going on. Okay, so if you then go to the check tab right? So the first thing I am recommending here is to go to the deform shape. This deform shape can be only activated if you go and activate either equivalent stress or plastic strain, and then after you can add, you can activate the mesh and deform view. Okay. So here we are seeing some big scale. Oop. Let's see what it's going on there. I think that's the beam that it's connected. Let me see what it's going on here. If I go to design, oh, I know what it's going on here. So remember that I use a gap here. Then if I go to transparent view, as you can see, this is not being connected properly or welded, right? Even if I use the cut and the welds are added there, I have to decrease that gap to have well connected the flange of the beam to the stiffener of the beam, right? So this is the case where I saw the deformation, and then I am seeing that something is not going correctly, right? So let's go to FP1, that it's the fin plate, and let's decrease the gap there. So that will be 7/8. Let's see if that works. A little bit less, maybe 3/4 here, right? Okay, then I can see if that's yeah, I can see the weld there again, right? So for this test, as I am doing testing, as I recommend you, then you can change that stop at limit strain going into cut setup. Okay, so you click OK, and then you calculate, and let's see if that worked. That is connected. So this is a case where I firstly check the deformed shape, because imagine if I go and start increasing the blades and or bolts or something related with the connection, but I didn't notice that the problem, as you can see here, it was the weld, right? There wasn't a weld there. So then if I go to check and then again see the form shape, let me increase the scale of the form. So now this looks okay, right? Well, as I would expect. Then after that, this is, well, the form shape is okay of what I was thinking, then I can go and check the blades, right? What is failing, as you can see here, is the end plate, right? Also then the bolts, B1 and B2 are failing. Then if you go to see the ball forces, you can see the direction of ball forces into the, well, you can see here the direction of the ball forces in the end plate and in all the connection. And also, if you click here, drop down menu, you will see the AISC checks, right? So forces of the bolts are from the finite element analysis, and then those are checked against the AISC equations, right? The same for the welds. So this is where you will need to either increase the bolts or increase the thickness of the blade. So let's go back into design and change this end plate. Instead of flush, let's try an extended one and then calculate again, right? So this is like the iteration that we are doing. As you can see, this was faster, right? Then talking about this traffic light, you will see that we have gray color. Gray color means that the elements that are in gray are under 60% of utilization. Green is above 60% and under 95%. And then red, well, you can imagine that it's something that it's failing. So this is very useful when you have, for example, these stiffeners that maybe you can delete those, and that will, well, you can optimize your connection, right? So you can go there to the stiffener operation and put it just in the front of the connection, and this will work okay. And if you're doing tests with some connections, you can also copy that connection and then do test in the second one, right, to optimize the design. If not, you can stay with the same first design. Okay, so that's the first example. I have to go to the second example because time is going faster. And okay, so let's go to the second one. The intention of this second example is to show you that we can handle connections, well, 3D joints, right? As David mentioned, we can analyze the full 3D joint. You can have in one node or in one joint the 4 connections of four elements, and also the bracing connection, right? So you're analyzing the full model. Okay, so the intention of this is not to show you how to model this, because I could spend hours and hours talking about modeling, right? But the intention was to show results, right? So imagine you finish this, and then you're okay with modeling, and then you run the analysis. Then you go to the check tab, and again, this is important to show. Well, here you will see also the importance of seeing firstly the deformed shape rather than seeing results in plates or bolts, right? Because firstly you need to fix that. So if we saw this in this view, we see that the formation of these beams are okay, right? But then if you go and see this this lateral view for the beams that are here, you will see that you're seeing, well, you will see an upward deformation, and we have only a shear force in the negative direction, right? So we expect to have a downwards deformation. So it is important because this issue or this thing happens very often with some cases that I receive. So they are more worried, let's say, to fix the connection rather than to fix this bad deformation, right? So firstly, the first thing I check when I have these cases is deformation. So why it's happening this? Well, if you go to the design tab again, and then you see the load effects into B3, or let me see, what is the B4? As I mentioned, only shear force is there. So what happens there is that when you go to those members, you will see firstly that model type is the one that will help, will help shear forces and moment forces. In this case, this element is going to only accept shear forces and maybe axial forces, right? So that's the first thing you will need to change. Then the second item that you will need to change is the bolts, the forces in. So in this case, we have forces in, well, we had before that in node, but here the correct option is to put it into the bolts. Why? Because that will create the hinge really where it will happen in the real life. That will be into the bolts, right? So let me show you now the before, and let's change it to the node. And you will see the difference in this wireframe view. And then if you go to the load effect, and then let's see this one. So this is creating the hinge into the bolts. And then if you go to the before, you will see that here it's having also a moment and also at the end of the beam, right? So the correct location of the force when you have only shear force in one member is where the hinge in real life will happen. In this case, the bolts, right? So let me go back to B3 and add it to bolts before and add it to bolts again and change the model type. And also the correct thing for the bracing will be the same, like changing to this model type. Because those bracings are only going to be deformed, well, only going to accept axial forces. Then after that, you can, again, let me stop at limit strain, calculate, and then you will get a reasonable deformation, and then after that you can modify your design to well, comply with the AISC and complying with not having any plastic strain more than 5%. Right? So hopefully this was this is, you understand this final part. If not, you can do some you can ask some questions. Let's see if we have some. Jan, do we have?
Yes. Yep.
Well, this is running.
Sure. Well, I guess we can start with some of the questions that David already responded to in the chat.
Okay. Yeah, we can
The
maybe
first one,
comment those. Yeah, sorry.
The first one was, can we bring a connection from a IFC model and how to do so? David, if you want to take this one.
Sorry, I didn't have my mic on. Yeah, so we don't currently have the ability to import an IFC model into IDEA. A big part of that is just the fact that depending on which software the IFC comes from, it can have a variety of different information. There's really, even though it's a neutral file format, there's different levels of it. So we just haven't kind of looked at that yet. The bottom line is we've been kind of more focused on having direct links with other pieces of software.
Okay, thank you. The next question was that I would like to talk about was about the oversized holes, and then I'll step back and let Andrea show the model. Are the oversized holes going to be implemented in the version 22 of IDEA StatiCa?
Yeah, so as far as an actual like oversized hole element, there is not in version 22. We do have some workarounds in that you can adjust the bolt assemblies when you get into the materials tab in the software. You can basically copy a bolt assembly and adjust the actual size of the hole that's being punched for that bolt size. So you can kind of create your own bolt assembly for the oversized hole at this point.
Okay, awesome. And I'll let you take it over, Andrea.
Yeah, just for the final part, because I am seeing good questions in the chat, but and maybe we can comment some of them. All right, so yeah, then after those changes, then if you go to the check tab, then you will see that now we have a reasonable deformation, right? Then now that you're happy with that deformation, then you can worry about maybe adding more bolts here or increase thickness of plates, right? So then you can start doing your design. Also, I am not sure if I have time, but this is something I wanted to show, guys. This is the last tip for the modeling part. So let's say you go and copy this connection, right? And you want to change the connection of this element to the web of the column, right? So let's delete the operations of that connection, okay? Right? And you remember you work in one connection that was similar to this, right? So we have this feature that it's called connection browser. So that is that you can save your own templates. Imagine you work in a very specific connection, so you publish that connection, and then you can use in a new model, right? So how does that work? So let's say I already have that connection published in the connection browser. Then you go and propose, right? So in this case, it says you don't have any suitable template for this specific geometry. So but I have the connection for these two members. So you can use the selection option, then you click here and then select the column, and using Control key, you click in OK button. Then you will find all the templates we have, and also into your private file folder, right? So you click in that one that I worked before, and then you apply it. So I have this built in before, and I use the same sections. So if you use the same sections, will work like smoothly. But maybe if you have a shorter, well, let's say a 12 section for the beam, maybe you can do some adjustments. But this is very useful to save your own templates, right? So, well, with that, I finish the demonstration, and then we can follow up with some questions.
Yeah, there's one question about the section cuts. Is there any update regarding the full assembly drawing in different views? So if you don't mind showing them how to create section cuts, I think that could be very useful.
Yeah, so let's put this view. So when you are here into the visualization area, you can just right click into the member and you create the section, right? So you can either zoom in, zoom out, and then you can save this view, right? And later in the report, you will see that you can call that picture, right? I didn't go further into the report, but we can plan a webinar to talk about it, right? But yeah, that's how you do that.
Awesome. There was also a question about the use of the asterisk when it comes to the bolt placement. I'll just take this one. So that asterisk allows you to, it's a shortcut to place the bolts. So using David's example, if you have 5 bolts that are placed at 3 inches from each other, then you can just do 3 inches times 5, and you will have those bolts all spaced at the same spacing. It's just a shortcut. You could just type 3, then space, then 3, then space, etc. That would be the exact same thing. There was a question about, yes, importing the complex shape from a DXF file. How could you do that, Andrea?
Importing
from DXF.
Yeah. So the option that we have for that, let's say, let me get that view, right? we can bring I mean, I can refer that to the plates, right?
Yeah, one of the plates.
Yes, one of the plates. All right. So imagine you want to add a particular design for a stiffening plate or a gusset plate, right? So you can go to the stiffening plate operation, and there you can see, let me put it in transparent view. You can see the plate that I just add, and that can be related either to joint, member, or a plate, right? But you then can change that shape and use the polygon option. So from polygon option, you can bring that DXF, and that will bring, let me see if I have something here, because I, let me go to this, because I have something here, yeah. So let me open this plate HSS. So you click here in consecutive, then you outline that one. So be sure that you have the correct units there, right? So again, outline, and then you can also add openings if it has that. I draw this in CAD software and then save it as that. And then, oh, I didn't bring in the correct. Let me go again and open that. So that's inches, because I draw in inches consecutive, outline, and OK. So now you can see this particular plate, and you can locate it using these coordinates.
Awesome. Okay. David, should we be taking more questions? Do you have anything you want to finish with?
I think,
no, I mean, we had a bunch of good questions that came in. I know we're out of time actually already. So definitely please feel free to reach out to any of us with any other questions. Anybody that did submit a question, we will respond back to you, either by email or directly in the chat right now. But I appreciate everyone attending. This was a great first webinar for the US team here, and we're planning on many more throughout the course of the year. So I hope you can join us again, and appreciate your time, and I'll let you get back to your day. Thank you.
Thank you. Bye.